Saxon's Calculus Lesson 87 is about L'Hopital's rule and then the proof of his rule. And he was a French mathematician, and so his name is pronounced uniquely, not exactly as it looks like it should. So the H is extremely silent, L'Hopital. All right, so his rule basically says when I am trying to find a limit and I have a zero that ends up in the denominator, I want a way to fix it. And so here's what he came up with on the bottom of 427 in the box. If you have a function a and another, so f of a and another function g of a, and both equal 0 or both equal positive and negative infinity, and if the limit as it approaches a, you can derive f's equation and derive g's equation, and that answer exists, then that is the limit. Okay, so now on page 428, example 1, we're looking to find the limit of x approaches 0 when we have cosine of x minus 1 over x squared. So if I just tried to plug in the 0, I would get a 1. 1 minus 1 is 0, which is fine, but 0 squared is not okay to have a 0 in the denominator, so I'm stuck. So his rule says, what happens if I derive this top? Well, cosine goes to negative sine of x, the 1 drops off, and then x squared becomes 2x. Can I plug in 0 now? Nope, still have a problem. Oh, derive it again then. So negative sine would go to negative cosine of x, and then this would go to 2. Now, when I plug in 0, I get the 1, and so negative 1 over 2, yay, I finally have an actual answer. So his rule helps unlock that 0 denominator problem. Example 2, find the limit as x approaches 0 if I have x cubed minus 4x over x squared minus 2x. So if I put the 0 in, yep, got a problem, so let's derive. So this becomes 3x squared minus 4 over top of 2x minus 2. Now, if I plug in the 0, that goes away, that leaves negative 4. 0 here leaves negative 2, and negative 4 divided by negative 2 is 2, and there is our limit. Example 3, find the limit x approaching 1 when I'm given natural log of x over 2 minus 2x. So if I plug in the 1, obviously I have a problem. So when I derive natural log of x, I get 1 over x. And then we're deriving this part. The 2 drops off, and the other is minus 2. And I can't have a fraction over a fraction. So I'm going to treat this as a fraction, flip it over and multiply it. So this becomes negative 1 over 2. So that is negative 1 over 2x. Then if I plug in 1, negative 1 over 2 is negative 1/2. I have taken it to an answer. Example 4. Find the limit as x approaches infinity, cosine of x plus 2x over 6x squared. Now, I'm not plugging in a specific number, I'm plugging in infinity. So when I plug in the infinity, I realize that cosine of whatever numbers I'm plugging in cannot give me answers that are more or less than positive 1 and negative 1, if you're picturing your cosine graph starting at the high point of 1, negative 1 is the low point. But these numbers, as I plug in infinity, just get bigger and bigger and bigger. So I can't really find a boundary for that. So we apply the rule. Let's derive cosine to negative sine of x plus 2 over 12x. Now what happens if we plug in infinities? this sign is still bounding with 1, but 1 plus 2 would make a 3. And then this number, as it gets bigger and bigger and bigger, and I'm dividing by a huge number. So if I have a small number divided by a huge number, that is getting like 0.00000 something. So we basically say that is going to the 0. Now the proof, of course, I'm not going to do, but if I take a quick look, I see that I am plugging into that basic f of x minus f of a over top of x minus a, and I'm doing that for both of the equations and then doing some algebra flipping around and so forth.